Hello students, in this video we'll see an example of changing a triple integral into spherical coordinates. Let's consider the integral. We're going to integrate x from 0 to 1. We're going to integrate y from 0 to the square root of 1 minus x squared. And we're going to integrate z from 0 to the square root of 1 minus x squared minus y squared. And then we're going to do this. We're going to do e to the x squared plus y squared plus z squared. And then I'm going to take this and I'm going to square root it like so. I'm going to do a dz, dy, dx. So this integral looks very messy to compute, but rather than doing this integral in Cartesian coordinates, we can plot this region of integration and see what's going on. Z goes from 0 up to the square root of 1 minus x squared minus y squared. That tells me that at the top limit of integration that z is equal to the square root of 1 minus x squared minus y squared, or that z is equal to 1 minus x squared minus y squared, which is equivalent to x squared plus y squared plus z squared is 1. So z goes from 0 up to the unit sphere. Where does y go from? Y goes from 0 up to what? Y goes from 0 up to this square root over here. And that's the same as saying that x squared plus y squared is equal to 1. So y goes from 0 up to this unit circle. So if we're to plot this region of integration, what we have is this. We have the y-axis, we have the x-axis, and we have the z-axis. Every variable x, y, and z is non-negative, so we're in the first octant. So this is a first octant problem. First octant. Everything happens in the first octant. X goes between 0 and 1, and y goes between 0 and the unit circle. So there's x equals 1, and this is the unit circle. This is x squared plus y squared is equal to 1. Then for every point down over here in the xy plane, z starts on the xy plane and goes up to the unit sphere. So let's draw the unit sphere. Like that. So there's my unit sphere, or at least the part of the unit sphere that lies in the first octant. And so z is going from here up to here, so that's our region of integration. So basically I'm in the first octant and inside the unit sphere. So our region of integration is the part of the unit sphere in the first octant. Okay? And if I turn this region into spherical coordinates, let's recall what spherical coordinates are. Spherical coordinates are x equals rho cosine theta sine phi. Y is equal to rho sine theta sine phi. And z is equal to rho cosine phi. That's my spherical coordinate change of variables. And with this change of variables, we know that dx, dy, dz transforms to rho squared sine phi, d rho, d phi, d theta. So let's change our problem into spherical coordinates and see what happens. So in spherical coordinates, what will we have? Our integral will turn into what? Well, what's happening for theta? In this region of integration, theta goes between 0 and pi over 2. Rho goes between 0 and pi over 2. The rho is the angle, the phi is the angle with respect to the positive z-axis. That goes between 0 and pi over 2. The theta goes between 0 and pi over 2. So I have theta going between 0 and pi over 2. I have rho going between 0 and pi over 2. I have my phi rather between 0 and pi over 2. I have my radius, rho, going between 0 and 1. Then I have e to the what? That's going to be e to the, this x squared plus y squared plus z squared is rho squared, so this is e to the rho. And then I have a what? Then I have a rho squared sine phi d rho d phi, d theta. And now we can box separate this. By box separation, this is going to be the integral from 0 to pi over 2 of d theta. There's no theta functions over here, so just get plain old d theta. Then again, integral from 0 to pi over 2 of the sine of phi, d phi. And finally, an integral from 0 to 1 of e to the rho, rho squared, d rho. So this first integral over here gives me pi over 2. This integral over here gives me a 1 because the area under 1 crest of sine is equal to 2. So the area under 1/2 crest of sine is equal to 1. So I have pi over 2. And then I have to do this integration by parts over here. So this is going to be my v over here. That's going to be my dv. And that's going to be my u. So if we integrate that by parts, let's do this row integral first. So that will be what? That row integral is going to give me a, so we have a pi over 2. And then we have a u times v, so that's rho squared e to the rho, because v is equal to e to the rho, from 0 up to 1, minus the integral from 0 to 1 of v, which is e to the rho, du, which is 2u e to the rho d rho, and that's going to be a rho. 2 rho e to the rho. So when I plug in 0, I get nothing. When I plug in 1, I get an e. So this is pi over 2. Then over here, this is going to simplify just to e. And then over here now, this is going to be my what? Over here, this is going to be my u, and this is going to be my dv. So we're going to have a minus. Then we're going to have a u times v. So that's going to be a 2 rho e to the rho from 0 to 1, minus the integral from 0 to 1 of 2 e to the rho d rho. Okay? So again, if we simplify this, what will we get? We'll get a pi over 2. Then we'll have an e. And then this expression over here is going to be, when I plug in 0, I get nothing. When I plug in 1, I'm going to get a 2e, so minus 2e, plus what? Plus, that's going to turn to a e to the rho, so I have a minus, which turns into a plus, and a derivative of 2e to the rho is just going to be 2e to the rho from 0 up to 1. When I plug in 1, I'm going to get a 2e. So that top limit is going to cancel out with this over here. And the bottom limit is going to be a minus 2. So this whole answer over here is going to be pi over 2. And I'm going to have an e. The top limit cancels, and I get a, when I plug in the bottom, I'm going to get a negative 2. So the e minus 2. And so pi over 2 e minus 2 is our desired integral. So we see by changing this integral into spherical coordinates, the limits of integration simplified dramatically. They simplified from very complex radical expressions just to a box in spherical coordinates, because we're in a portion of a sphere. We're in the portion of the unit sphere where the angular variable theta is between 0 and pi over 2, and the longitudinal variable phi is between 0 and pi over 2 as well. And since we're in a perfect sphere, the radius rho goes between 0 and 1, turning me into a box. Then the only thing that happens is, even for a complex function like this, I only have one integration by parts to do, because there's only one function of phi and no functions of theta. So box separation applies since I'm in a box or a rectangle in spherical coordinates. Thank you very much.